Hello, thank you for joining this session. I'm Gianmario Spacagna and I'm the Chief Scientist of Helixa. So today I would like to share with you some of the engineering practices that we have been using at Helixa while building machine learning systems. All right, let's start. So what you're going to learn in the next 20 minutes is about a real machine learning system that is powering a platform used by thousands of marketers around the globe. And you will also see a bunch of tools and engineering practices that enable us to build fast, cheap, and robust pipelines. Okay, before we start with the technical details, let me give you a little bit of context. Helixa is an audience intelligence platform that uses machine learning to provide accurate consumer insights for modern market research. So in order to understand what kind of insights we are providing, let me guide you through an example. Let's suppose that we want to analyze the OpenAI audience. And first thing we'll see is that this audience is 1.5 million people. And what the platform will provide you is a list of demographics like distributions. So we can see that this audience is between 80 and 40 years old, is mostly male, and is located in US and India. In addition to demographics, we will also calculate who are the top influencers based on affinity scores. And we will also do the same for getting the top media and the top products and companies. So this is the output of the real-time analytics application on Helixa. Now let's look what is behind it. When we built this platform, we had to keep in mind a few requirements. So first thing was we need to build something that works for multiple datasets, that can provide accurate insights, real-time, quickly, but at the same time, it also has to be always available, cost-effective, and does not have to require a lot of infrastructure maintenance. Okay, so now let's see what this system looks like. The end-to-end pipeline starts with data integrations. So we'll start with exporting data from external data sources and then converting it into a common data model that is digestible by our algorithms. And the machine learning jobs in our case are in sequence. We first do some contents embedding, then we do entity resolution. The entities are then categorized in one of our taxonomy, and then the interaction between users and entities is used for creating the digital DNA that is a representation of the users that is used for predicting missing traits, as well as for augmenting latent interest. And then the output of those machine learning jobs are used for powering the real-time analytics applications. Okay, now let's have a look at the broad architecture here. As we have seen before, we have some data ingestions, that are ETLs, that will store the data into the data lake, such that the machine learning pipelines can read the data and can interact with external cloud services. For example, we use the Google AI services for language and vision, but as well as we also use pre-trained models, as well as external APIs for location and most of the most popular machine learning libraries. As part of the jobs, we're gonna create some models and store them into repository. And the deployment is going to be either through batch jobs or through microservices. The final outputs are then stored into the production DB that will enable the analytics applications. Okay, this is the whole architecture. And in order to implement that, we had to use a bunch of tools for each component of the system, for different stages. Today, we're gonna focus on everything but the machine learning libraries, because the goal of this talk is not to tell you how to build models, but everything else that is required in order to integrate those models within the whole system. Okay, let's start digging into the single components. So we'll start with the data lake. The first decision we made was to not use any Hadoop file system, but instead storing all of our data in S3, such that we would use Glue for crawling the artifacts that we save in S3 and building the data catalog. And we would use Athena on top of it to build all of the logical views. I'll show you some examples how the data looks like in our feature store, for example. In the feature store, we will start partitioning the data with the feature family. So in this example, we are creating some text embeddings for the users. So that is going to be the name of the feature family. And then the second level, it will be the timestamp when that particular run of the feature extraction was when that dataset was created. And inside it, we will store some metadata as a JSON file, and the actual data will be in Parquet indexed by user ID. If we're storing labels, it's a slightly different partition scheme. We will have variables, that is the variable we want to predict, like in this example, the gender, and then we will use a second level for partitioning based on the source from where we extracted the ground truth. And we will also use an external tool that is Snort for managing the label extraction, especially for weak labels. In case of predictions, it's a very similar schema, but we will use the model identifier to partition the prediction that were created by that particular model. Okay, all right. So now that we have seen, we got an overview of what kind of data is in our data lake. Now let's see how the development works here. The first suggestion I want to make is to use platforms for managing the life cycle of the machine learning models. And at Helixa, we have been using SageMaker and MLflow extensively in production, and I strongly recommend them. But we also use other tools like Paperspace and CML, especially for experimental work and research and development. So the workflow for R&D is the following. We always, most of the time, we write code locally in our laptop using professional IDEs. And then we would use the Git flow branching model based on Jira keys and save the data in a central code repository in GitHub. Then we would SSH, so start our own machine in the cloud, pulling the latest version of the code, spinning the Jupyter server, then installing the latest version of the code locally, and saving the data and sharing the notebooks in S3. But instead of reading directly from the S3 data storage, we will go through a layer of cache through Alluxio. So the configuration we used for the Alluxio cache was EC2 machines. We use EC2 machines that are optimized for memory, and we assign them 250 gigabytes at least, of which 200 gigabytes are reserved for the Alluxio cache. So in this 200 gigabytes, we would mount our S3 buckets locally using the Fuse API in read-only mode. And that means that now we can access the data in multi-processing, for example, using Dask, directly from the local file system without having to go through the Boto API. The benefits of using this configuration is that if we do some quick calculation for a small team of data scientists, we would end up with more than 500,000 read requests every month to a single S3 objects that are files. And using Alluxio, we observed a speed up between 3 to 5 times. So that was really helpful during the R&D. Nevertheless, there are use cases where you just cannot load the whole data in memory. You're processing a data set that is larger than your memory. So in that case, it doesn't make sense to cache the data locally in the server. Instead, we would integrate the Jupyter notebook with EMR, Elastic MapReduce, through Levi. And we would just delegate all the computation to Spark through ephemeral clusters on Spot instances. And this is a smart way to save costs and have a pool of machines doing all the heavy calculation. All right, so we have implemented our jobs. Now let's look at how the deployment looks like. In order to simplify and speed up the deployment, we would structure the code base into modules and entry points that represent executable tasks. And those tasks are packed and shipped as Docker containers. Now, the next step is going to be execute those tasks, and we try to avoid as much as possible or human intervention in our numerical processing, so we delegate to the continuous integration. We use CML and Circle CI such that every time we do any commit in any branch, we will run the code test, and every time we do a release on the master branch, we will then trigger the builds and the deployments, as well as the testing and the generation of evaluation reports. Okay, now let's see what those deployment infrastructure are that we're using for executing those tasks. If you're doing some embarrassingly parallel massive data processing, I recommend you to look at AWS batch. The way it works is that your data is divided into batches of roughly a few gigabytes each, and each batch is mapped into its own Docker container, its own job into the Docker container, which are sent to a queue, and the AWS batch will eventually process those jobs and consume the queue and execute the containers. And you don't need to manage any infrastructure. Everything is managed by Amazon. There are other use cases where you want to do more, for example, model serving, you need a microservice for that. It's not a bad job, it's more like something, a runtime kind of job. So you can either use ECS or Kubernetes. Those are two very good choices for orchestrating containers, but you have to make some choice about where you're gonna, what kind of provisioning you wanna use underneath. And my recommendation is to start with a Fargate, which is a serverless choice. You don't need to care about anything. No need to manage any of those infrastructure, but you are limited. You can only deploy containers with max 4 CPUs and 30 gigabytes of RAM. So if that doesn't fit your needs, you want to go for the serverless choice with AWS EC2 machines. That is, of course, is more advanced, is more powerful, more customizable, but it requires infrastructure management. All right, now the big question here is, how do containers behave when they have to deal with a changing request load in a real-time application? So let's suppose that this is the chart of how many requests per second we receive every second. We can set the capacity at like 4 times the actual demand, and that works fine for 99% of the cases. But then there is a sudden burst, and your system is not able to deal with it, and is not able to scale quick enough to meet the demand. And this is, for example, what happened a few days ago when the PlayStation 5 was released in the UK, and most of the websites for those online stores, they crashed because they couldn't handle the number of requests. So there's also another problem, actually, that even if you don't hit this threshold, you're still paying for all of the over provisioning, even though you're not using it. Right. So what could be a valid alternative to that? We can do real-time model serving in a serverless way. We need a little bit more preparation work during the training phase, and I'll show you how. So when you do the training, you will save the model, of course, but you will also package the requirements for the later inference, all of the libraries that you've been using. And then you will update some metastore with the new configurations, as well as deploying a Lambda function, one or many Lambda functions, such that when you have a new request, the API gateway will trigger the Lambda function, which is going to look up all the information needs about the user and the model have to use, will read the features, will get the model, load the libraries, and then produce the predictions. This is an alternative way of doing model serving. So what are the benefits of using Lambda functions? First of all, they scale by design based on the real-time demand. And this is possible because the provisioning time is measured in seconds, not minutes. And because by default, they are concurrent up to 3,000 concurrent executions. And if the burst persists, that number is going to increase by 500 every minute. So Amazon did this great job on making sure that the Lambda are, almost always available and can scale to any demand. In addition to that, you also gonna pay only for what you use. That is really effective from a cost point of view. And in our use cases, we managed to spend like 10 times what we used to when we had our own machines always up and running 24 hours. There are some downsides, of course, and the biggest one is that each single function can only do very little small chunk of work, can only use 3 gigabytes of memory, and you cannot really do any multiprocessing there. Moreover, the execution has to finish within 15 minutes. So those are two big limitations that may not fit your needs. So when you need to decide, you really need to consider everything, whether you want to use containers or Lambda functions. Since they both have, pros and cons, why not making the best of it and possible, especially using this amazing orchestration framework called step functions that essentially allows you to create any custom workflow by integrating different services. And it supports almost every possible service in the Amazon ecosystem, including Lambda, Batch, and all of the container deployment services. All right. So if you're really going to use step functions a lot, especially with Lambda function, I recommend you to look into the serverless framework, which will cut most of the boilerplate code. Okay, let me just quickly show you what tools you can use for monitoring and alerting after you've done the deployment. So the first thing is to collect logs, and there is really great stack based on the Elasticsearch that you can use for collecting and visualizing the logs, and I really recommend you to be using that. If instead you want to, you need to do some monitoring of the infrastructure, you can start with the basic monitoring provided by CloudWatch. But if you need something more advanced, you want to look into Datadog. That is a general infrastructure monitoring tool. But if you're looking for something serverless specific, you may want to consider also Tableau. And in addition to the monitoring of the infrastructure, you also want to monitor the KPIs and the metrics of your algorithms. So there's very quick solution that works out of the box. That is Amazon Quick Site that is based on top of Athena SQL queries. But you need to do some more custom and programmatic look into this Dash framework. We arrived toward the end of this talk, so let me summarize what we have seen so far. We probably have realized that the machine learning code is only a tiny bit of a broader and more complex system that we need to consider when designing those kind of problems. Especially if you're a startup, is that when you are doing a lot of machine learning, advancement, and innovation, you may want to move fast. But if you don't care about the infrastructure, that's going to hurt your business in the long run. So always move fast, but with stable infrastructure. That's really important. How do you do that? We have seen there are a lot of tools. Probably you already knew some of them or most of them, but I hope that you learned something today. As well as we have seen there are good engineering practices they can use for having a very stable, robust system. And if you never used serverless architectures before, then that might be a good time to start, looking into this new paradigm. All right. So if you want to, get more details, I know you're curious about building machine learning products, you can go on the Helixa website. You can download this non-technical guide, which will cover everything from a non-technical point of view that we have not covered today. And that's it for today, and thank you very much.